So the question says, a cardboard box without a lid must be constructed from a sheet of cardboard of length 1 meter and width 0.75 meters. What would the dimensions of the box be to contain the maximum volume possible? Square corners should be cut out of the cardboard sheet to form the sides. And we have the formula: volume is equal to length times breadth times height. And they say the diagram is not drawn to scale. So that's basically our question, and with the accompanying diagram. So the box that we're going to produce from this sheet of cardboard is going to look like this red box that I've tried to sketch here, with its length, breadth, and height as shown here in this red diagram. Now, one thing to note is that we can express the length L in terms of h. So we can see that that side, which is 1 meter long, can be expressed as 1 meter is equal to L plus 2h. From what we can see there on the diagram. So the length 1 meter is made up of L and 2h, and the length 0.5 meters is made up of B and 2h's. So therefore, we would have 0.75 equal to B plus 2h. Now we can take 1 equal to L plus 2h and make L the subject of the formula. So it becomes L is equal to 1 minus 2h. And likewise, we can also take 0.75 equal to B plus 2h and make B the subject of the formula, and it becomes B is equal to 0.75 minus 2h. So we have L equal to 1 minus 2h and B equal to 0.75 minus 2h. Now with that, we go to our formula for volume, which says V equal to L times B times h. In place of L, we substitute 1 minus 2h because we have established that L is equal to 1 minus 2h. In place of B, we substitute 0.75 minus 2h, and the h. We go ahead and simplify that, and in the final step, we would get 4h to the power 3 is equal to 7 over 2h squared plus 3 over 4h. You will notice that in this working, I changed 0.75 to 3 over 4. It's just that I think that 3 over 4 is easier to work with than 0.75. Now the next step, because we talked about maximum volume, whenever we talk about maximum in this question under differentiation, we should know that we differentiate the volume with respect to h to get dV dh, which is equal to 12h squared minus 7h plus 3 over 4. We get this by doing the whole thing of power multiplied by coefficient and then subtracting 1 from the power. Now at maximum, dV dh should be equal to 0. So 12h squared minus 7h plus 3 over 4 is equal to 0. Now we solve that equation, that quadratic equation. To solve the quadratic equation, we use the quadratic formula, which in our case here says h is equal to minus b plus or minus square root of b squared minus 4ac all over 2a. Now our a is 12, our b is negative 7, and our c is 3 over 4. We substitute all of that in the formula. Once we substitute and we simplify everything, in the end we'll find h is equal to 7 plus or minus square root of 13 over 24. If I use that to solve for h, I get two values of h. One value is h is equal to 0.44 meters, and the other value is h equal to 0.14 meters. Now remember, in the beginning I had expressed my L and B in terms of h. We saw earlier that L is equal to 1 minus 2h and B is equal to 0.75 minus 2h. Now in these two little equations, we substitute the values of h that we found here. If I substitute the value of h, which is 0.44, into the equation for L, I find that L will be equal to 0.12 meters. If I substitute 0.14 into the equation for L, I find that L is equal to 0.72 meters. To find B, I substitute the two values of h, and for the first value 0.44, I find B equal to a negative number, negative 0.13 meters. And for the value 0.14 meters for h, I find B equal to 0.47 meters. Now you can see that the value of h, which is 0.44 meters, has given me a negative value for b. Since b is representing length, it cannot be negative. So then we have to drop all the values associated with 0.44, which means our final dimensions, which give us the maximum volume, are h equal to 0.14 meters, L equal to 0.72 meters, and B equal to 0.47 meters. That's the solution.